Hello everyone. This is a lecture about carbon allotropes. So this is very interesting for us because whatever we have learned till now, all about the hybridization of carbon materials, all about the different crystal structures of carbon materials, that is going to be used here. Now we are trying to understand different allotropes of carbon. What is an allotrope? If you remember, allotrope basically means if an element is available in different physical forms, and these physical forms are typically because of different crystal structures. However, the element itself, the chemical formula itself is the same, but physically they are different crystal structures. For example, diamond and graphite. In that case, we call them two different allotropes of the same element. Okay, so there is another word, isotope, which we learned a couple of classes back. Isotope is when we are talking at an atomic level, in fact, nuclear level. Then these are isotopes. Allotropes are at crystal structure, crystal level. Okay. Now in this context, you will also hear another term which is known as polymorph. So you will also read that graphite and diamond are two polymorphs of carbon. So what is a polymorph? Polymorph also indicates the same thing, that you have different physical or crystalline forms, but the same chemical formula. The only difference is that polymorph is a more general term. So you can also use it, for example, to indicate some compounds. But the term allotrope is specifically used for elements. So this is the only difference. You can understand that all allotropes can be called polymorphs, but not all polymorphs can be called allotropes. Okay. Now, we are going to use the term allotrope mostly in this particular course. One reason, of course, is that because we are going to always talk about elemental carbon. The other reason is also that the term polymorphism is used very differently in different branches of science. For example, in the case of biology, you indicate different phenotypes as different as the two polymorphs. So, for example, maybe I should show this with a picture. The yellow tiger and the white tiger are considered the genetic polymorphs of each other. Similarly, in the case of object-oriented programming, the idea of accessing different objects but with the same interface, that idea is known as polymorphism. In the case of medicine, you have a certain type of data in ECG which is known as a polymorph. In all cases, however, we are somehow trying to indicate that it's the same thing but the physical forms are different. The idea of being same but different is somehow indicated by the term polymorph. But we are going to, in this particular course anyway, use the term allotrope. If you are more interested in learning about the difference of polymorph and allotrope and how these terms are exchangeably used, there is a review article that you can read. Okay. Now we come to the carbon allotropes. So I told you, I think before, that when I was in school, which if I think of it, it was like 20 years ago. When I was in school, we were taught only diamond and graphite as the two allotropes of carbon. But nowadays, fullerenes are also taught as the carbon allotropes, which is good. Okay. However, we should know that these are only primary allotropes of carbon, and then there can be also many compounds, elements, many materials which are in between, which have this SPX hybridization state, and which we can have between these elements as well. So carbon materials are actually it's like a periodic table, So you know that these materials should exist, but there were so many materials, so many elements in the periodic table, for example, which were not discovered at that time when the periodic table was formulated. But people left some blank spaces for them. And then later on, now because we can already guess the properties or the type of those elements, then it became easier to guess them or to find them, and later on many of those elements were discovered. So something like that is also true for carbon elements. Carbon allotropes, elemental carbon forms. This is also true, and now we know that there are different hybridization states, and based on that we can have large number of carbon allotropes. So, however, now we have three primary allotropes, which are diamond, graphite, and fullerenes. You know that fullerene is not just one type of ball. One C60 is that the Buckminster fullerene is not the only fullerene. We know that. We also can have a range of them. We can have different sizes, different curvatures, and at some point the fullerene will not exist anymore. The structure will collapse. Now we know all of these things. So you should keep these things in mind. Also, graphite can have slightly graphite-related elements, or diamond can have diamond-like carbon, which we will learn in this course. This is the idea. We learn about all the, not just these different carbon forms, but also their technological applications. This is what we are going to learn. So now, before we go into that, we need to understand how do we classify the allotropes. One more interesting question is that should graphene be called an allotrope instead of graphite? Are graphene different anyway? You know that graphene and graphite, yes, they are different because graphene is the single sheet, graphite is, it contains multiple sheets. Even the more important difference between the two is that the graphene sheets are randomly organized on top of each other, while graphite has this A-type order in its, and that is how you have the crystal structure. Now, we know that. But should then we call graphene and graphite, should we, designate them as different carbon allotropes? This is an interesting question. In fact, in the literature here and there, you will see that there are, three or two primary carbon allotropes, and people say it is diamond and graphene and fullerene. So, in my personal opinion, it should be graphite and not graphene. The reason is that, number one, graphite has a certain fixed arrangement of crystal, which is not the case with graphene, because graphene itself can have a lot of variations. Because, as I said, they're randomly oriented sheets, so they can be oriented in infinite different ways, number one. And number two, also, the definition of graphene is also not very clear. It should ideally be a single sheet without any defects. So, but in many cases, in technological applications, you will often not have the single graphene sheet. You will often have multi-layer graphene, what they call. You will also often have a lot of defects. So, this is something that we cannot completely define, or at least we cannot reach a consensus that exactly this should be called graphene. So, for graphite, however, we know that what is the crystal arrangement. We also know that, how to process graphite. We know what kind of, crystal faults it has. For example, stacking faults, you can have line defects, you can have, so we know so many things about graphite, and that is why. Also, the fact that graphite is naturally available and we can mine it, and we can, we know a lot about it. So, let's call graphite and diamond and fullerenes as three primary allotropes, but of course these are only primary allotropes that we know. We know that there are many more, carbon materials that can exist. Now we are going to use this approach, the hybridization based approach, for classifying the carbon allotropes. It's in fact one of the biggest difficulties in teaching carbon is that there are so many carbon materials, and if we directly start with the material itself and the properties of the material itself and the manufacturability of the material itself, then we often cannot study other carbon allotropes in the same context. Then we end up studying only one carbon material, and we cannot study, or we cannot relate different carbon allotropes with each other. So what we are going to do here is we are going to do this hybridization based classification. After that, we will go into individual carbon materials. So in the lectures, in the next 2-3 slides, you're going to hear also some names of carbon materials that you might not have heard before. Or, some of these are in fact very fancy names. And in fact, this is a good question whether or not we should call them allotropes. But if you understand how they are hybridized and how, at a crystal level, how do they look like, then it doesn't matter whether you call them an allotrope or not. Okay, so this I mentioned before. Every day, scientists are coming up with new different types of carbons. Carbons, by the way, this term also here and there I will use. Carbons, which you will not use probably for any other element. You will not say coppers or irons. At least I have not heard that. But carbons it's like a plural of carbon, because you see there are so many carbon materials available in the nature. Then you don't always say carbon materials. You sometimes just say carbons. Okay, so many carbons are being discovered every day. We don't even know if they are, when we are discovering them, maybe they were already existing, but in another form or a slightly different form. But we are definitely developing techniques of making them, artificially making these, different types of carbons. And that is why you can say that every day a new name is being added to the list of carbon allotropes. But we know there are 3 primary ones. And it's also confusing a little bit sometimes. The nomenclature becomes confusing because you have even graphene and graphite. I would say the nomenclature is a little bit confusing here. But the point is that new types of carbon materials with different properties and probably also different hybridization states are being discovered every other day. So here are some examples, and I would like you to do some more internet search and try to find out what are the new carbon materials, the different carbon materials. You will see a lot of names. So some of them are even very fancy. When you say, oh, this is carbon onions, okay, then you will see, or you will think about, of course, you can imagine what an onion is, and it should have some sort of layered structures, which is true, and that is because of its similarities to the physical structure of onions. It was given the name carbon onions. Now, if I ask you, what do you think is the hybridization state in the case of an onion? That is a difficult question, because also then you need to know the exact curvature of onion. Not all onions have the same curvature, right? But these are because of the similarities with certain things. Whatever is the best way to describe the materials, that is how the names are given. And every day you will then see many different names coming up, and many compounds many elements are similar to graphene. Many of them are made by folded graphene or curved graphene and so on. So you can read about it. Okay. Now the question, as I said, what is not really known in the case of many of these new carbon forms, you can call them allotropes. What is not known is the exact hybridization states. The properties are known. If you can physically make something, then you can measure the properties. This is always the case. So then you can also back calculate the hybridization to some extent. Okay. So, 3 primary hybridization states and 3 primary allotropes. Okay. Now, if I give you bulk solid carbon, bulk solid carbon, you can understand. Then I'm not talking at nanoscale. I'm not talking at microscale either. I'm not talking about the individual crystal units, or not talking about individual molecules. I'm talking about a powder or a bulk solid, a piece of carbon, if that is given to you. Okay. In that case, if you are given a piece of diamond, then all the atoms are sp3 hybridized, most likely, or most of the atoms. If I give you a piece of graphite, well, or pure graphite, so in that case, most of the atoms are sp2 hybridized. But there are many other carbon materials which will have all types of atoms in them. Even if you take coal as an example, if I, let's say, remove the impurities from coal, if I just take elemental carbon, which is in that kind of disordered structure. Now, when you say disordered structure, you know that you have some crystalline parts and you have some non-crystalline parts. In the crystalline parts, you will then have sp2 hybridization, for example. But in the non-crystalline parts, you don't know. You might even find traces of sp3 carbon. You might find traces of sp2 carbon. You might find sp2 plus N for sure, especially if you have some curved structures, which is most of the time that is the case with the disordered carbons. So you will have these materials. If you talk about them in bulk, then you can call them mixed carbon allotropes. So this is the terminology that I have used here, because I thought about what is the best way of describing such carbon materials. So I think we can just call them mixed, because we don't know also exactly in this bulk carbon form what exactly is the hybridization state for each individual carbon. And it's also very difficult, because even each sample might significantly differ from each other. So we just call them, in this course, we are going to call them mixed carbon allotropes. Okay. For example, so here are two pictures where you would see the scale bar is 5 nanometer. So this is where you can actually see. What can you see? You can see the microstructure of carbon in these images. These are transmission electron microscope images. Okay. So now in this case, you see that both of these images indicate somehow an sp2 type carbon. So whenever you see these lines where you see, here, these are basically crystal planes. And these are sp2 type planes, which just by looking at the image you cannot say. You have to do some other calculations. You have to see what is the distance between these two planes. If it is perfectly, if it is graphite, then it is, then the layer separation will be different compared to when it is not graphite, but slightly it is graphitic carbon. So you see, these both are images of sp2 type carbon. But one of them is crystalline and the other one is disordered. But even in the second image, you see in the disordered image also, you see some of these lines. So regions of that material are graphitized or are graphite-like. So in the second image, now you will say, in the first image you can say that, okay, most of the carbon atoms are sp2 hybridized, so we just call it sp2 type carbon. Second one, we will say is a mixed carbon allotrope because it has sp2, but it also seems to have other type of hybridization states that we don't know of. We just call them amorphous when we don't know of them, So these are amorphous regions and crystalline regions. That is how we call it. But within the amorphous region, we don't know each individual atom, what is happening to it. Okay, so these types, so the second image, these types of allotropes, we'll call them mixed carbon allotropes. Okay, so all in all, what we are going to do is we are going to have like these 5 different columns, let's say, for the classification of carbon allotropes based on sp3, 2, 1, sp2 plus n, because that is a known thing to some extent, and then whatever is left over, whatever we call it mixed carbon allotropes. Okay, so here it is. Allotropes of carbon. As I mentioned, we have these 5 columns I have prepared. Okay. And in this column, I'm going to first write the family of allotrope. So again, this entire thing it's a new nomenclature. I'm not calling diamond and graphite a single, graphite as one allotrope and diamond as one allotrope. I mean, of course, they are in their pure forms, but I'm indicating that there is a graphite family. And there is a diamond family, and there is a fullerene family. So we call them allotrope families, where the primary allotrope, of course, is also a part of that family, the main member of that family. So graphite, diamond, carbide. I have written it in this dashed box because, this is still something which is being discovered right now. So this is carbide family. sp2 plus n, I did not write fullerene, I rather wrote curved carbons, as I mentioned before, because in order to avoid the confusion, fullerenes you will always think of just the spherical ball-like structure, but curved carbons can be other curved structures as well. For example, carbon nanotubes. So curved carbons. Now, we also have, at the end, we have the mixed carbon allotrope. In most cases, mixed carbon allotropes are disordered carbons. So that is the primary member of that family. Okay. So these are the main members. How about the further, other members of that family? In the case of carbine, we don't quite know. So carbine is the only kind of the known member of that family, if at all. However, in the case of graphite, you have a lot of, so graphite on top, what I have written is the main member of the family, but then we also have graphene, which you know now is the actually structural unit of graphite. But the only thing is that it's not as organized as graphite when it comes to bulk form. Now, you also have some other names here. If I explain all of them in this lecture, this is going to be a very long lecture. So the idea is that by the end of this course, you will know about all of these different carbon materials. For now, out of interest, you can just do a quick internet search and see what do these elements, what do these forms of carbon mean. So pyrolytic carbon, then carbon fibers, you know, but not all carbon fibers are graphitic. So some of them are also disordered. That's why I said some carbon fibers. There is something called graphite whiskers. There are many other elemental forms that can be put in the graphite family. So you can learn about it on your own. In the case of Curved carbon, of course, the primary member is the Buckminster fullerene. Carbon nanotubes are also, as I said, they are more closer to graphite than to fullerenes. But since they are curved, I have written it here. This will give you the, this explains that they do not have pure sp2 hybridization. There's some slight curve due to the curvature. They have a slightly different hybridization state. Okay. Now, diamond, what is diamond-like carbon? It's carbon which is like diamond, but it's still not diamond. So this is also we are going to learn in this course. There is also something called lonsdaleite, which is a form of carbon, which is a form of diamond, something between maybe diamond and graphite, but closer to diamond. Okay, we are going to learn about all of these things. Disordered carbon, of course, can have a lot of, so there is no primary member in the case of disordered carbon, but there is something called non-graphitizing carbons, and we'll learn about that. Non-graphitizing carbon are very important for us because for when you make micro nano devices, actually you are pretty much always using the non-graphitizing carbon. So what is also for battery applications, for supercapacitor manufacturing and so on, it is mainly the non-graphitizing carbons that are used. So this is also something that we are going to learn. In fact, you will often hear commercially they say that these are graphite fibers or graphite batteries. Graphite battery you must have heard a lot. It is not really graphite. It is close to graphite, but it is this non-graphitizing carbon which may have parts of its structure, like I showed in this previous TEM image. Parts of it are graphitized, so they have this graphite-like crystal arrangement, but they are actually disordered carbons. So all of these things we are going to learn, but the idea I hope you understand is that we have a certain allotrope family and we have different members, and I think if we have these 5 different families, then we should be able to put everything in here. Even if you come up with a new carbon material, then you should be able to place it on this chart, so to say. So as I mentioned before, this is like a periodic table. The elements the forms that I have mentioned, they are the known forms. There may be many other known forms also which I have missed out. But we can also always find more forms of carbon, elemental carbon, and then we can put it on this chart, and then maybe in another 20, 30, 50 years we'll have a much longer list. Okay, so there is something. This is another interesting thing is that we know that there is sp2 plus n, so there's something between sp2 and sp3 that we know, but do we know something between sp1 and 2? In my personal opinion, that should also exist when we have something between 2 and 3. But the point is that right now we don't even know sp1 carbine type of carbon structures properly. So first that needs to be discovered, and then we will probably go into what is between sp1 and sp2, and in fact there can be something between sp1 and sp3 also, which is also an interesting thing. So all of these materials are yet to be discovered. So this is our sort of very, very basic periodic table of carbon. Okay. Now, I would like you to do a few things on your own. So first of all, as I said, all these, the carbon materials, the names that I have written, do a quick internet search and try to find it for yourself what these materials are. Then as I also said that, can you try to find more materials than what we have on this chart? Because definitely there are more materials. Okay, and now you take some of these other materials, which, for example, I said carbon onions in the previous slide, but I don't think I have shown carbon onions here. So try to figure out what carbon onions are. What could potentially be their hybridization state? Are they of mixed hybridization state, or are they primarily curved carbon type of carbon? If they have a lot of graphite-like structure, then will you put them in the graphite family, or will you put these materials in the curved carbon family? If you think that they have mixed hybridization, or we don't know anything about their hybridization, then maybe we could also put them in the the disordered carbon family. But this is something, maybe it will be a good exercise if you do it by yourself. Okay, so in the context of this hybridization-based classification of carbon allotropes, we also have another diagram which is a triangular diagram. So what I showed in the previous slide, which is something which I prepared these different columns. That is something, there are 5 different types of allotropes, which makes it easier because then you have 5 primary families, and then you have other materials you can fill in. But there can also be more complex representations. So this particular representation, for example, this was already suggested by someone. So you see this carbine and carbanoid structures. I had also given this reference in the context of carbine when we were talking about them. So in this book, in the preface of this book, in fact, this kind of diagram was suggested, which gives rise to some interesting questions. So first of all, do we have anything between SP and SP3? So as I also said before that we don't know right now. SP and SP2 also we don't know actually. So we only know this SP2 plus N. So fullerene structures. They are between 2 and 3. If I also think that if there's something that exists between 2 and 3, there should also be between 1 and 2. Something should be there. But should we also have something between 1 and 3? That's also a good question. So we do know some. So here and there you will read about some super diamonds or graphines, and I'm sorry, but these names are just confusing people a little bit more, because now graphines, there's so many. I'm not saying that it's wrong that we find these elements, and it's very nice and it's very interesting if we have very completely new properties, or if we can even synthesize these kind of allotropic forms of carbon. Very good, wonderful. But sometimes the names become confusing. Because now if somebody starts doing his or her research on graphines, now it is very important that that person first understands graphite and then graphene and then the allotropic forms of carbon and the classification of carbon allotropes, and only after that you when you know this picture is clear in your mind, then you think of whatever is the new thing. You can give it any name, but what is more important that you fundamentally, in terms of hybridization, you understand it. But this anyway is a good classification, because here we see that there is a possibility of finding something between SP2 and SP3, SP and SP3 or SP and SP2, and these are the things which are still, we don't know them yet. And these are, in research, maybe one of you in the future will find one such, new allotrope of carbon. Okay, so these are some interesting questions that arise. We also don't know so much about these super diamonds. I personally also, some of the names that are written here, I also don't know, because as I said, that these terminologies are a little bit confusing, and so I may not know these materials by their names. I do probably understand how they look like and what should be their properties, but I may not really know the names, because the names are being coined every other day. So also you guys don't get confused about it. The point is that it will be nice if you can try to Google or try to do some little internet search about these names and then figure it out for yourself what is what. Okay. Now, the most important question here, and also the previous chart that I have shown, is that whether can we actually have this kind of chart where we can have a periodic table like thing where we can discover further forms of carbon, we can fill in the gaps. So can we number one, can we do that? Can we actually make them? Can we synthesize these kind of carbon materials? That is question number one. Question two is that if we cannot synthesize them, can we at least theoretically predict them? I personally think yes. If we understand the hybridization, that is very strong, then you can definitely predict new carbon materials, and then at some point they may or may not exist, because it is quite possible that theoretically they are possible, but in reality their energy of formation is too high, or they are very unstable. But at the same time, theoretically it should be possible to predict. So these are the questions that you can also think of. The very idea in this lecture was to tell you that the best way to classify, to clean up the mess a little bit when it comes to carbon materials, the best option is to classify them based on their hybridization states.